Today we're going to be covering the Chapter 2 review questions from Discovering Design with Physics. As I said with the Chapter 1 questions, my goal in these questions and covering these for you is to help give you tools so that you can work to be able to solve these yourselves. So number one, I want you to try to work all of these problems first before you come to these videos, and then come to the videos and use them to check your work and potentially help you with any problems that you struggled with. The second thing is that I'm not going to be covering things that you can quite easily find in the book, because that's not a good use of our time here. So for questions like number 1 here, where it's just define a couple terms, you can easily find those answers in the book just looking them up, and so I'm going to skip those. Today I'm also going to skip number 2 because even though it's not listed with the definition terms, this question is really asking for definitions that you can find in the book as well. So let's start with question 3. An object is experiencing a net force that varies. Can the equations of motion derived in this chapter be used to analyze its motion? So for this question, if you're taking good notes, you already know the answer to this. And by taking good notes, I mean one of the suggestions that Dr. Wile gives is to always take notes of anything that is highlighted red or dark pink in the book. And so on page 48, there is a box that says the equations of motions in this chapter apply only when the acceleration is constant. So if a net force is varying, the acceleration is also varying and therefore not constant. And so our answer here is no. The equations of motion from this chapter cannot be used to analyze the motion of this object. I'm not going to write that down because it's just writing down what I just said, but that is the answer to question 3. So now for question 4. An object starts off with an acceleration of 2.3 feet per square second, but after 10 seconds it begins traveling with a constant velocity. It travels at that constant velocity for a full minute. Then it says if you use equation 2.1 to determine its acceleration over the entire 70 seconds, will your answer be 2.3 feet per square second? And if not, will it be greater or less than 2.3 feet per square second? So you've already noticed probably that I have highlighted a couple words here. Those are acceleration and velocity. And the reason I highlighted those is because they are vector quantities. That gives me, whenever I am reading a problem, just a little tingle in my brain that tells me when I finish writing the answer that I might need to make sure that I've included some kind of direction, because these are vector quantities, okay? And so that is just a practice that I have that just helps give me a reminder to look and see if a direction is needed in my answer, or even as part of the equation when I'm working out the equation. Now, not all of the time will a direction be needed as part of the answer. It depends on what the question is asking for. So for example, the equation for acceleration includes time. Time is not a vector quantity. So if the question is actually asking about time, I wouldn't need to have a direction in there. Okay, so that is what that highlighting means, and I'll be doing it throughout these review questions. So let's go ahead and refer to equation 2.1 since it asks us about that in the question. So you can see here, this is part of my notes that I take. I like to take a separate page of notes for all of the equations that I need. So they're all in one place. Okay, I label them with the number that they're given in the book. I give them a title because the book does not give these equations titles. And some of them are pretty simple. So acceleration, for example, well, A stands for acceleration, and that's what this equation is about. Force, F stands for force, and that's what this equation is about. So I give those titles. Those are pretty simple. But there are other ones that it's really helpful to give a title that kind of explains what the equation is about. And we'll see more of these later. But so for equation 2.1, our equation is acceleration equals the change in velocity divided by the change in time. So our starting off, we are given the acceleration, but we're not given anything about the velocity. We know the acceleration is positive. It is 2.3 feet per second squared. Then it says after 10 seconds, it begins traveling with a constant velocity. So a constant velocity means if we have a 0 here, because our start and end velocity from this 10 seconds until for the full minute, so for 60 seconds, it's going to be 0 divided by 60 is our acceleration during that second period of time. We aren't given enough information in this first period of time other than to say what this change in velocity was. We wouldn't know what the initial or final velocity was, but we are given what the initial acceleration is. And with this information, about from 10 seconds to 70 seconds, we know during that second period of time, the acceleration had to be 0, because 0 divided by our period of time, 60 seconds, is going to be 0 feet per second squared for the acceleration. And I'm not writing this down because with that 0 there, you can pretty easily just figure that out in your head. So the question is asking us over the entire 70 seconds, would our answer be 2.3 feet per second squared? So this is a yes or no question. This is why I'm not writing down any of the numbers. And if not, will it be greater than or less than 2.3 feet per second squared? So it's not asking us to actually calculate anything here. And so our answer for this is that for this first question, will your answer be 2.3 feet per second? No. And what this is actually trying to determine is an average over the entire 70 seconds. So our average acceleration would not be 2.3 feet per second squared. And that's because our initial is 2.3, and then for that next 60 seconds, it's 0. And so the overall acceleration over this entire period of time is going to have to be less than 2.3 feet per second squared. Okay. Then the next question, if not, we said not, will it be greater than or less than 2.3 per second, or 2.3 feet per second squared? And it will be less than 2.3 feet per second squared. So that's our answer for that. No actual calculations really required. It's just thinking through that problem and realizing what it's asking for. Okay. So now for question 5. In the graph on the right, positive means north. Okay, so I'm going to highlight that because that is telling me something about the vector quantities. Positive means north. It asks me at what times is the acceleration 0. So let's look at what is being graphed here. We have velocity on the y-axis and time on the x-axis. Okay. Whenever the slope is positive, then that acceleration is positive. Okay, and that's because the velocity is changing in a positive direction. Okay, whenever the slope is negative, the velocity is also negative because the velocity is changing in a negative direction. Whenever the slope is 0, such as right here, or and I should say it's changing from positive to negative, okay? Then the acceleration then is 0. The acceleration is also shifting from positive to negative, okay? And so at what times is the acceleration 0? Here's where it shifts from positive to negative here and here. And this is negative to positive, okay? And so now we have to figure out what numbers we have to write here because there's some estimation that needs to go on right here. And right here, we just need to make sure that we have a good number of significant figures, okay? So how far we can estimate these, because these grid lines are every 10, we need to go 1 decimal place over. And so we can estimate these to the nearest ones digit, okay? So I should say digit instead of decimal place. So grid lines are to the tens place. The estimation has to be to the ones place, okay? And our significant figures need to reflect that as well, okay? So I'm going to estimate that this is 8 seconds, okay? And so my answer is that the acceleration is 0 at 8 seconds. And now, so what I'm saying is that our significant figures need to go to the ones place. If I just write 20 seconds, 2 would be my only significant figure, and that is not going to the ones place, okay? And so the best practice for this would actually to put this in scientific notation to show that this 0 is a significant figure. So I'm going to say 2.0 times 10 to the 1 seconds. Okay. So the acceleration is 0 at 8 seconds and 2.0 times 10 to the 1 second. Now, you notice that the slope does change here, okay? And so I want to point this out. Yes, the slope changes, but it is positive in both cases. It is not switching from negative to positive. And so therefore the acceleration at this point is not 0, okay? So B for this question, during what time intervals is the object moving south? Okay, so since positive means north, any negative velocities mean that the object is moving south. Okay, and so it doesn't have to be the slope is negative, okay? As long as the velocity itself is positive, it is moving in a positive direction. As long as it is negative, it is moving in a negative direction. Okay, so we're going to look here for this question at what times the velocity is actually negative. Okay, and so here's our 0, and these are the only points where our object is having a negative velocity. Okay. And so once again, I'm going to estimate here. Okay. And so I would estimate that this is 16 seconds. and this is probably about 15 seconds. If you're off by a digit, that is fine. This is an estimate, and that is okay. All right. Oh, and that shouldn't be 15. Sorry, this should be 25, right? Because 25. Okay. So my answer here then is the object is moving south from 16 seconds to 25 seconds. Okay. During what time intervals is the object slowing down? Okay. So an object is slowing down whenever the acceleration is opposite of the velocity. Okay, so if the velocity is positive, as it is from 0 to 16 seconds here, then the object is slowing down when the slope changes and becomes negative. Okay, so we have positive velocity, positive slope here. Here we have positive slope, or positive velocity and negative slope here. So from 8 seconds to 16 seconds, that is when this object is slowing down. It is still going in that northerly direction, but it is slowing down. Okay. From 16 seconds to 25 seconds, the object is having a negative velocity. And so once again, we're going to look for where the velocity and the acceleration are opposite in sign. Okay, so from 20 seconds to 25 seconds, we have a negative velocity but a positive slope. So this object is moving in a southerly direction, but it is slowing down here and about to start moving in a northern direction again once that velocity goes above 0. And so then from 25 to 40 seconds, the velocity is positive again, and the acceleration is also positive. The slope is also positive. Okay? So the answer from this is the object is slowing down from 8 seconds to 16 seconds. That's where we had a positive velocity and negative slope. And we're going to use this same notation, 2.0 times 10 to the 1 second. So from 20 seconds to 25 seconds is where it has a negative velocity but a positive slope. Okay, and that is C. And then finally we have, what is the instantaneous acceleration at 25 seconds? Okay, so 25 seconds, we're going to look at this line segment where we have a straight line that does not change in slope. Okay. And so we're going to be using our equation 2.1. This is just our simple acceleration equation, right? Where acceleration equals the change in velocity divided by the change in time. Okay, so acceleration equals, I'm going to go ahead and plug in these numbers. So my change in velocity, you're always going to take the final velocity, and it can be anywhere along this line, minus the velocity that occurred previously. Okay, so what is easiest for me here is I'm going to take this one here. Okay, and so my estimate is that at this end point of this line segment, my velocity is 12. Okay, because my scale is from 10 to 20, so 12. And our units are meters per second. So final velocity minus whatever the initial velocity that I take. And I am going to go ahead and take what I see at the 20 seconds, okay? So I estimate that this velocity is about negative 15 meters per second. Okay, so it's minus a negative 15 meters per second, okay? Which would be the same as just adding it. And then time. Time, I make sure that you take the same points, okay? So my time at this point where I took that final velocity, I estimate is about 29 seconds and 20 seconds. And if I wanted to, I could write that as the 2.0 times 10 to the first seconds. But I'm just going to remember that I'm dealing with two significant figures here, okay? And so when I calculate all of that out, I'm going to get a total of 27 meters per second divided by 9 seconds. And those seconds don't cancel. They actually end up as seconds squared. So when I do 27 divided by 9, I get 3 meters per second squared. Okay, now why do I have just 3? Well, that's because this 9 is a single significant figure. And why do I keep this a single significant figure? Well, that's because our rules for addition and subtraction, which we did right here, tell us that you don't do number of significant figures, you go by the decimal place, okay? And so this is to the nearest ones digit where our significant figures are. And so here I'm not going to go 2 significant figures even though I have 2 for each of these, because it's subtracting. I'm just going to the ones place, which is the most precise that these are significant, okay? And so then when I divide, I do have to say 1 significant figure in my answer, okay? So then my final answer for this is the instantaneous. And you know what? I didn't do something that I told you I was going to do. That this is a vector quantity, okay? So the instantaneous acceleration at 25 seconds equals. Now, I didn't include any of the directions in here because what we have on here is that positive means north, okay? And so all of this was already converted into whatever sign, meaning north or south. And so just in my answer, I need to convert it back, okay? So the instantaneous acceleration at 25 seconds is 3 meters per second squared, and this is positive, and so my answer is 3 meters per second squared north. Okay. Question E, over what time intervals can our equations of motion be applied to this object? Okay, and so that's going back to our third question where we looked on page 48 where it says that the equations of motion in this chapter apply only when the acceleration is constant. So that means that we must have a constant slope. Okay, and so from 0 to 20 seconds, we do not have a constant slope. These are curved lines, okay? So we cannot use any of our equations of motion in this chapter in this interval from 0 to 20 seconds. But from 20 seconds to, we said, did we estimate this one? I don't think we did. To this point here, we have a straight line that we have a single slope. From here to 40 seconds, we also have a single slope. Okay, so I'm going to estimate that this is about 28 seconds. Again, if you're off by 1 or so, then that's fine. And then this one's obviously 40 seconds. Okay, so our equations of motion can be applied, and we're going to write both time intervals separately. Okay, applied from, so we had this 2.0 seconds times 10 to the 10, or 10 to the 1, 2.0 seconds, oh, sorry, 2.0 times 10 to the 1 seconds, so we said 28 seconds, and from our second time interval starts at 28 seconds to this 40 seconds. And the 40, we're going to do exactly like we did with the 20. We just need to have the significant figures to the ones place. So we're going to say 4.0 times 10 to the 1 seconds. Okay, and that is our answer for 5E. So now moving on to question 6. An object is accelerating west at 3.4 meters per second squared due to a force pushing at 1.2 newtons. What is the object's mass and what is the direction of the force? Okay, so first thing I'm going to do is go in and highlight my vector quantities. Okay, so we're accelerating and I'm given a direction, so this is really important, and then my question is asking about direction, or second part of the question. So my first part is what is the object's mass, and then the second part is the direction of the force. Okay, so I didn't do this in the first chapter, but as we go on, these equations are there's going to be a lot more equations in your head, and it sometimes helps to just write out the information you know, and then figure out what equation you can use to solve what you are looking for. Okay, so what we know, acceleration is west. Whenever I see the direction in the question, I'm going to immediately assign it a positive or negative, okay? And I typically assign whichever direction I see first to be the positive direction, okay? So anytime I see a positive number in one of these vector quantities, I am knowing that it's moving west, okay? So my acceleration is west at 3.4 meters per second squared. So I'm going to write that down. A equals 3.40 meters per second squared. Okay. I see a force is pushing at 1.2 newtons, and newtons is a unit of force. Okay. So my force, my capital F, equals 1.2. Now, I'm not going to write newtons because when I get into this equation, newtons is not easily used in factor label conversion method. And instead, I want to write what units make up newtons. So in my equations, newtons and pounds are not one of the labeled numbered equations in the book, but they're going to be so important for being able to use these equations that I included them in this sheet. Okay. And so the units for newtons are, if we break it down, is kilograms times meters per second squared. Okay. And so instead of writing newtons for the force, I'm going to write what newtons breaks down into. So kilograms times meters per second squared. That is my force. Okay. And then what is unknown is mass, because that's what the question is asking. Mass equals, actually, I'm going to put it under here. Mass equals question mark. Okay. And so now I have listed out and labeled everything that I know and everything that I don't know that I need to know. Okay. And then having that, I can use my bank in my head or in my list of equations and figure out which equation is going to help me solve this mass question. Okay. And so here, equation 2.2 for force. Force equals the mass times the acceleration, right? I have two of the three here, so I'm going to be able to easily solve for mass. Okay. So let's plug that in. Force equals mass times acceleration. So my force is 1.2 kilograms meters per second squared equals, my mass is unknown, times my acceleration, 3.40 meters per second square. I'm going to divide both sides by 3.40 meters per second squared. Okay, meters per second squared is going to cancel out on both of these. Right, and 3.40 will cancel. And so what I'm going to be left with is this 1.2 divided by 3.4 kilograms equals the mass. Okay, and so when I do that math out, I get 0.35 kilograms equals the mass. Okay. I'm going to check my significant figures. At the end of any of these problems, I'm checking that I did significant figures correctly. Okay. So everything was multiplication division in this problem. So I'm using the rules. That's the total number of significant figures of the value that has the least amount of significant figures. So that would be the 1.2 newtons here. So 2 total significant figures, and I have 2 total significant figures here. Everything to the left of this decimal point, because it's 0, is not a significant figure. So 0.35 kilograms is correct as far as significant figures. Okay. And so now, as I told you last time, I like to write all my answers out in complete sentences because it's just another chance for your brain to be like, hold up, like units aren't correct, or I'm not answering the question that's being asked. Okay. So the object's mass is 0.35 kilograms. Okay. And the force is going to also be west. Okay. Force and acceleration are always in the same direction. So the force is west. Okay. Force and acceleration are always in the same direction. So since the acceleration is west, then the force is also west. So finally, going to check and make sure I answered the question being asked. Okay, I had two questions. What is the object's mass? The object's mass is 0.35 kilograms. Kilograms is a mass unit. And what is the direction of the force? The force is west. Okay, not following instructions, not reading the entire question and answering all of the answers that's being asked for. And that's my number one mistake students make that lose them points, especially the students that are really smart and think they understand everything great, and they do understand everything great, but then they get so fast and they forget to actually read the question and answer what's being asked for. Okay, question 7. A 15.0 gram object is being pushed west with a constant force of 1.76 newtons. If it started from rest, what will its velocity be after 5.1 seconds? Okay, so let's start out with writing out what we have and then determining what equation is going to help us determine what we need to find out. So in our final question here, what will its velocity be after 5.1 seconds? So what will its velocity be? Okay, so 15.0 grams object. So that is a mass value. So I'm going to say M equals 15.0 grams. Okay, we know it's being pushed west, and I've just gone ahead and defined west as positive. My force is 1.76 newtons. Force equals, I'm going to change that unit to the completely written out units of newtons, which, as we said before, is kilograms times meters divided by seconds squared. If it started from rest, okay, so that means that we have an initial velocity here, okay? So velocity not equals 0 meters per second. What will its velocity be after 5.1 seconds? So my delta t, my total time that has transpired, is 5.1 seconds. Okay. So I have mass, I have force, and those go into the only equations I have to work with that is this right here, this force equation. And so I can find out the acceleration there, but that's not what it's asking me for, right? It's asking me for the velocity. And I have the initial velocity, and I have the time, total time. What it's asking me for is the final velocity after that 5.1 seconds has transpired. And so what I'm going to need here is actually both of these equations, okay? So what I'm going to have to do first is to get this final velocity, I need to figure out what the acceleration is, okay? Because here I'm missing two things, right? I'm missing the final velocity, which is part of the change in velocity. We have the final velocity minus the initial velocity. And I'm missing the acceleration. Here with force, I'm missing only the acceleration, but if I find out this acceleration, I can plug it in here and figure out the rest of this that I need here, okay? So I'm going to start with my force equals mass times acceleration. Force equals mass times acceleration. So let's plug that in. I have 1.76 kilograms meters per second squared equals, my mass is 15.0 grams. And I just realized I have grams and kilograms here. So I'm gonna have to do some conversion here. Okay, the easiest conversion that is gonna be is just getting it into what this newtons is. Okay. You could go the opposite way, but I'm going to just change this grams to kilograms. Okay. So instead of 15.0 grams, I'm going to multiply that times, or divide it, divide it by 1,000 and turn it into kilograms. So it's going to be 0.123, right? There's the fast method. Okay, so 0.0150. Notice I still put this 0 here because it is a significant figure, and that's going to help me. Kilograms. Okay, times the acceleration. Now I'm going to divide both sides by the 0.0150 kilograms. Kilograms will cancel. And I'm going to be left with this divided value, meters per second squared equals the acceleration. Okay. And so my final acceleration is going to be 117 meters per second squared equals acceleration. Okay, so now I can plug in acceleration, 117 meters per second squared. Okay, and I don't recall whether your calculator spits out a number that has more digits than this. It probably does, but we have 3 significant figures here, 3 significant figures here, so our answer for the acceleration needs to also be 3 significant figures because we're using multiplication division rules. Okay, so now I can plug these into my acceleration equation. So acceleration equals change in velocity divided by change in time, right? So my acceleration I just figured out is 117 meters per second squared equals my velocity final is what I don't know, but my initial is 0. And that's really handy when our initial velocity is 0 because it just makes things so much easier. You can just almost not even write it, but we're still going to write it. Okay, velocity final minus 0 meters per second, and our total time, our change in time is 5.1 seconds. Okay, and so like I said, you can pretty much not even use this, right? Just cross it out. And so now all I have to do is multiply both sides by 5.1 seconds to end up getting my final velocity by itself. Okay, and when I do that, I'm going to get 598 meters per second. Sorry, my seconds is going to, the single seconds will cancel with these. So, and then so I get meters per second, meters, and then just only one of the seconds canceled here equals my final velocity. Okay, so the velocity will be 598 oh, and I made a grave error here, so like I have shown you, we always need to check those significant figures. Okay, and that's kind of, as I was writing this, I was checking it. I was like, wait a second. So this seconds here we had 2 values. One was 3 significant figures, the other one is 2. And we're dividing, so the rule is to take the lowest number of significant figures. And so we need to round this to make it 2 significant figures. Now, if we round this, it says 600. Well, 600 has only 1 significant figure, okay? Because there's no decimal place here. And if you did put a decimal place, then it would be too many significant figures. It would be, if you put a decimal place, right, it would be 4 significant figures. So we don't want to do that. And so to show that we have 2 significant figures, we need to put this in scientific notation. So what we'll do instead, of 600, we're going to write 6.0 times 10 squared and meters per second. Okay, so now we can write that in 6.0 times 10 squared meters per second. Okay, and so now I'm going to check that I'm answering what was asked for. Okay, what will its velocity be? Oh, wait, velocity, I highlighted it. It's a vector quantity, and I did not put a direction. So this is why I suggest that you highlight this, because when you are just so excited that you've finally reached the end of this problem, you're going to forget to write the direction on it. Okay, so the velocity will be 6.0 times 10 to the squared. This is positive, and we've defined positive as west. And so yay, this saved me, right? So the velocity, so what it will be, that's our final velocity, 6.0 times 10 to the 10 squared meters per second. Meters per second is my unit of velocity, and I have my direction here. So this is my final answer. So now let's do question 8. A 1,710 kilogram car is traveling north at 25.0 meters per second. The driver hits the brakes and the car stops in 69.1 meters. What constant force did the brakes apply to the car? Okay, so I'm going to start highlighting and underlining here. Okay, I see a direction, north. I'm going to highlight that, and I'm going to define north as positive. I have meters per second. We've already had north. I know this is velocity, and that north is part of that velocity. The driver hits the brakes and the car stops in 69.1 meters. And then what constant force did the brakes apply to the car? So that is all my vector quantities that I really need to focus on. And constant force is what I am looking for. Okay, so let's write down all of the things that we know. Okay, we have mass, 1,710 kilograms. Mass. Okay, we have a velocity. Okay, and we know that the brakes are hit and the car is going to stop. So this is our initial velocity, V naught. 25.0 meters per second. Okay. The driver hits the brakes and the car stops. Okay, wait. So stops, that means we actually have, even though it wasn't stated, we have a second velocity. That's the final velocity, and it's 0. So velocity final equals 0 meters per second. Okay. And the distance that it took for it to stop was 69.1 meters. So this, you remember back from chapter 1, that is our delta x, that is our displacement, 69.1 meters. Okay, what constant force did the brakes apply to the car? So we don't have any extra information out of that. Now, we're being asked for force. So that is force equals mass times acceleration, right? We have the mass, but no, we don't have acceleration. So we can't immediately plug anything into this equation that we use to determine force yet. So what do we have that we could find out this acceleration so we can get this force value, okay? We have the initial and final velocity, and we have delta x, okay? And so from our equation sheet, okay, so we have this one here, and this one requires time, and we don't have time. So let's look at the next one, all right? We have a final velocity, initial velocity, acceleration, which we need to find out. But if this is the only thing that's missing, then that could still work, and delta x. So we have 3 of the 4 variables that are needed for this equation about acceleration and displacement. So let's use this then to determine the acceleration. Okay, so let's write this equation out. Vf squared, the velocity final squared, equals v naught squared plus 2a times delta x. Okay, and now we can just plug in. So our final velocity is 0 meters per second, and we're going to square that, even though we know what the answer to that's going to be, right? Equals, our initial velocity is 25.0 meters per second, and we're going to square that, plus 2, a is our unknown, so we're going to leave that as a variable, times delta x, 69.1 meters. Okay. Okay. So the easiest thing to start out here is, I know that this is gonna out, right? And so 25.0 meters per second squared is going to be 625 meters per second squared. I'm just going to go ahead and just move it over here. And it's actually 625 meters squared per second squared, right? Because that's squared, you're squaring both the meters and the seconds, okay? And so instead of just writing 0 equals this, I just move this over before I even calculated it, okay? Equals 2a times 69.1 meters. I'm going to divide both sides by 2 times 69.1 meters. Divide both sides by 2 times 69.1 meters. Okay, one of those meters is going to cancel, right? And then here, at 2 and 69.1 meters is going to cancel. And so I'm going to be left with A. And so when I do that, I'm going to get 4.52. And again, I might have gone further in the decimal places, but there's 3 significant figures. This 2 is a constant value, and so this does not count towards the significant figures count, so we're going to ignore that 2 as far as significant figures, and this is 3 significant figures. So my answer should be 3 for this acceleration. So 4.52 meters per second squared equals my acceleration. Okay. And, oh, and do not forget that this was negative. Okay, negative 4.52 meters per second square equals acceleration. Now I can plug this in to determine my force. So my force equals, my mass was 1,710 kilograms times negative 4.52 meters per second squared. And so my force is going to need to be 3 significant figures. Number 1, this is the lowest number of significant figures, but actually this is 3 also, right? Because we don't have a decimal place. So my force ultimately is 7,730 kilograms times meters per second squared. And this is negative, right? So now when I write it out, I'm going to use this negative to determine the direction, okay? So the brakes applied a constant force of 7,730. Notice I don't put the negative here because I'm going to put the direction, which has the same meaning, and it means more when you're writing this out in a sentence. Okay, so 7,730. Now I can convert this back to newtons, and so that's what I'm going to do here. Newtons, and it's negative, so it is south. Okay, brakes applied a constant force of 7,730 newtons south. Okay, so knowing what the units for newtons is going to be so important for these chapters, because if you have this memorized, you can easily just, oh, okay, this is newtons, and write out the correct units here, okay, and do the vice versa conversion, okay. So that is question 8. Now let's look at question 9. A 560 gram object is at rest if a constant force of 2.1 newtons west is applied. What will be its displacement after 9.6 seconds? Okay, so I have a west here. That force is a vector quantity. And I have a question asking about displacement, which is also going to require some kind of direction. Okay, and the displacement is my big question. What will be its displacement? All right, so now let's go through and write out all the information we have. We have 560 grams, so that is a mass value. And by the way, that is 2 significant figures. Okay, we have a constant force. So force equals 2.1 newtons. I'm going to go ahead and convert that. Kilograms times meters per second squared. Okay, and my question is asking about displacement. So delta x is a question, and my time, my delta t, equals 9.6 seconds. Now, one thing that I'm reading through this again, I forgot something. The object is at rest, okay? So and then a constant force is applied, and it's probably going to move when I apply constant force. So my initial velocity equals 0 meters per second. And my final velocity, I don't know. I don't know if I'm going to have to figure it out, but I know I don't know it, okay? So I need to know about displacement. That is what my ultimate equation should be? Do I have all of the information to determine that displacement? So let's look at this acceleration displacement equation. Okay, you need the final velocity. We don't have that. Initial velocity, we have that. And we don't have acceleration either. Okay, so we're missing a lot of stuff here. We have almost nothing for this equation. So this equation's not going to help us. Let's see. What about this one? So displacement related to initial velocity and acceleration. That might be more promising. So we're missing this, we know that. We have the initial velocity, great, it was 0. And then 1/2, we have the time, but we don't have acceleration. But do we have enough information to get us acceleration? And that answer is yes, we have force and mass. And so it's very simple for us to determine what the acceleration is. Okay, so we know from this, we're actually not going to need to have to find out what this final velocity is. So I don't need to worry about that one. But I do need to figure out what the acceleration is first before I can determine the displacement. Okay, so let's use our force equation. Force equals mass times acceleration. Okay, my force, 2.1 kilograms times meters per second squared equals my mass, 560 grams. I need to convert that to kilograms. Okay, so as soon as you see something with newtons, you know that if you're given a mass, you're going to need to convert it to kilograms. Okay, and I can do this one pretty easily in my head. So I'm just going to do this in my head. 0.560 kilograms. Okay, and I just did this in my head. Okay, 1, 2, 3. Okay, and actually I should just be writing 0.56 because this 0 is not significant. And I told you that as I was writing it down, right? Okay, 0.56 kilograms times acceleration. So divide both sides by 0.56 kilograms. Kilograms will cancel. Okay, and I am going to be left with 3.8 meters per second squared equals my acceleration. Okay, 2 significant figures, 2 significant figures, 2 significant figures. So now I can use this other displacement formula to determine what that delta x is going to be. Okay, so I'm going to write down the formula here. Delta x equals v naught times time plus 1/2 of the acceleration times time squared. And let's plug everything in. So my v naught is 0. And you know, at this point you could probably not even write the time and just okay, whatever. But I'm still going to go ahead and write it. 9.6 seconds. It's ultimately going to just be crossed out because you're multiplying times 0. But plus 1/2 of the area, 3.8 meters per second squared. I didn't give myself enough room here. Times the time, 9.6 seconds squared. Okay, sorry, I didn't give myself enough room. Okay, so not going to even worry about calculating that. Equals, when I plug all of this into my calculator, and don't forget to square those seconds squared are going to cancel, and you're going to be left with meters, which is exactly what we want. And so you're going to get 175 meters. Okay, but let's look at significant figures. We have 2 and 2. Okay, so we need to round this. Equals 180 meters. Okay, so now let's write out that answer. The displacement, and this is the great thing that I like about writing out your answer in a complete sentence. As I'm writing this, I see displacement and I'm thinking, oh, that's a vector quantity. I'm going to have to write a direction. Okay. And I'll still figure that out when I do this, but it's a great reminder. So the displacement will be 180 meters. And my direction, this is positive. And so I didn't write it here. I should have, but west was positive. Okay. 180 meters west. And that is our answer for question 9. For question 10, if something is falling near the surface of the earth, what is necessary in order to treat it as if it were in free fall? And so one of the equations that isn't really an equation that I wrote down on my equation sheet, because I just know we're going to be using it, is this acceleration due to gravity, right? So in metric units, it's 9.81 meters per second squared, and in English units is 32.2 feet per second. And the assumption is that it's down, okay? But in order for this to work, you have to assume that there is not any friction that is going on. And so what is necessary in order to treat it as if it were in free fall is that you either ignore the fact that there might be friction or resistance in the air, or so air resistance, or that it is very low. You assume that it is low, or that it will very easily overcome that friction or air resistance. So I'm not going to write down the answer there, but any answer that is kind of like that just basically says that that air resistance isn't a factor will work for this question. Question 11, 3 objects are dropped from the same height. Object A accelerates downward at 15.6 feet per second squared. Object B accelerates downward at 11.1 meters per second squared. Object C accelerates downward at 9.81 meters per second squared. Which object is in free fall and which is being pushed down as it falls, and which is being strongly affected by air resistance? So we have 3 questions here. Which object is in free fall, which is being pushed down as it falls, and which is being strongly affected by air resistance. Okay. So free fall is acceleration due to gravity, right? And just pull this up again, right? And 9.81 meters per second, that looks very familiar. That's object C. Okay. And so we know that object C is in free fall. Okay, so if something is accelerating faster than this, that means something else is helping it to fall down faster. If something is accelerating more slowly than this, then it is encountering air resistance. Okay. So let's see, 15, oh wait, this is in feet per second, and I just looked at meters per second. So let's look at the feet per second from my acceleration due to gravity. So 9.81 meters per second is the same as 32.2 feet per second. So object A is less acceleration than the acceleration due to gravity. So this is going to be the one that is being affected by air resistance. And object B, metric units here, is going faster or accelerating more quickly than object C, and so something is pushing on it. So object B is being pushed down as it falls. And object A is strongly affected by air resistance. It's about half of the normal acceleration due to gravity. Okay, so that is 11. Question 12. A 9 millimeter pistol shoots a bullet with a velocity of 1,150 feet per second straight up. Ignore air resistance. The question A asks us, what is the bullet's velocity at its maximum height? What is its acceleration? Okay. So let's write out what we know first. Okay. And okay, so we have, I see it as straight up. Okay, so I'm going to highlight up. You can make up positive or negative. To me, it makes sense to make it positive, right? But we just have to remember that down is negative, because here's the next thing. We know the acceleration. This question doesn't tell us anything about the acceleration, but we know it. Okay, so let's go back here first though. So this pistol shoots the bullet with a velocity of 1,150 feet per second. So that is its initial velocity coming out of the pistol. Velocity naught equals 1,150 feet per second. Okay. We know the acceleration because we are just dealing with gravity here. Okay. And so acceleration due to gravity, we're going to put this in English units because that is what our velocity is given in. And so our acceleration equals negative 32.2 feet per second squared. Okay, and the reason why this is negative is because we defined up as positive, and the acceleration due to gravity is always going down. Okay, so we're going to assign it a negative value. Okay. All right, so the velocity at the maximum height. So let's just draw this out. There's a pistol, it shoots the bullet, right? And then it's going to drop back down. Okay, so at its maximum height, the velocity is changing from positive up to negative down. So the velocity at the maximum height is 0. Not meters. Feet per second. Okay. Then what is its acceleration? Well, I just answered that, right? So the acceleration is negative 32.2. And actually, we're not going to put the negative because that doesn't mean much when you're putting things in a sentence. 32.2 feet per second squared down. Okay, and if I'm doing what I've been telling you to do, in this question, I'm highlighting that. Now, if the velocity is 0, you don't need to put a direction because it doesn't matter what direction. There is no direction at that point, right? And so we don't have to put up or down along with the 0 feet per second, but we do need to put it for the acceleration. Okay. For B, what is the bullet's velocity when it falls back down to the height at which it was shot? Okay, so in free fall, an object that is launched upward and then comes back down ends up at the same speed but going down when it reaches the height from which it was launched. Okay, so the velocity here, okay, let's do this. Velocity is 1,050 feet per second, but now instead of up, it is down. Okay, and you can say downward or whatever. Okay. So for question 12C, you'll forgive my edit because I have some of this highlighted already, but what is the bullet's maximum height relative to the height from which it was shot? Okay, so I have maximum height highlighted as a vector quantity because it's going to be up that we are referring to here. So let's think about what this looks like. Okay, let's go back to what I drew here. So the bullet is shot and the maximum height is right here, and then it's going down. So we're trying to determine what this height is right here. So there is actually a piece of information that we already determined here that might be able to help us, and that is that final velocity, because we know that at this maximum height, that velocity is going to be 0. Okay, and so we have acceleration, we have the initial velocity, and we have the final velocity, and we need to determine what the displacement is going to be. Okay, so let's look at our equations and see which one fits this. Okay, and so the first one I kind of automatically went to was this one, but we're missing too many things from this. We don't know anything about time. But here we do have the final velocity, we have the initial velocity, and we have the acceleration, and all we're missing is one variable, okay? And so we're going to use this equation about acceleration and displacement to determine the answer here, okay? So my velocity, I'm going to write out this equation. VF squared equals V naught squared plus 2 times acceleration times delta x. Okay, so my final velocity, 0 feet per second, equals my initial velocity, 1,150 feet per second. All of this is squared, plus 2 times the acceleration, negative 32.2 feet per second squared, times delta x, our unknown here. Okay, so like I did in one of the earlier problems, I'm going to calculate this part and move it up over automatically. And so I'm going to get a pretty big number here. It's going to be negative 132.500 feet squared second squared. Now, there are only 3 significant figures here. I'm going to wait until later to get this back down to the correct number of significant figures. Equals this 2 times negative 32.2, so it's negative 64.4 feet per second squared times delta x. Okay, and so now I can divide both sides by this negative 64.4 feet per second squared. Okay, and so one of my feet is going to cancel, both of my second squared will cancel, and I'm going to be left with delta x equals whatever this is. And what I end up with is 20,500 after I adjust for significant figures feet. So I should have 3 significant figures here. I have 3 with 1,150 feet. I have 3 with negative 32.2 feet. And then this is 0. So, okay, equals delta x. Okay, and so now to write this out, the okay, and in this one, it's a displacement question, and so it's like technically you should include a direction here, but just because we put the word maximum height, that tells you that it's up, okay? And so this would be perfectly acceptable as is. Maximum height is 20,500 feet. Question 13, you drop a heavy ball off the top of a building and it takes 1.28 seconds to hit the ground. What is the height of the building? Okay, so I don't see anything that is an obvious vector quantity here. There's some things that we know of gravity is going to be taken into account, and we are just going to assume it's down, right? And so we probably won't need anything positive, negative on this, okay? We're going to assume that positive is down with this one just to simplify, okay? So what do we know? We have time equals 1.28 seconds, okay? We know our initial velocity was 0. We're just dropping that ball and not throwing it with any force. Okay, so the initial velocity is meters per second. We don't know what the final velocity is. We do know acceleration. Acceleration equals 9.81 meters per second squared. Okay, and so let's look at our equations here. Okay, we don't know delta x. We do know initial velocity. We do know time. We know acceleration, and we know time. So this is going to be the one that we use. So delta x equals v naught times time plus 1/2 acceleration times squared. Okay, and so now we can plug in. Okay, for this one, I'm going to just not write anything here. All right, our v naught is 0, right? And time, it doesn't matter what time is because we're multiplying times 0. So I'm just going to ignore this one. Okay, it's great to go ahead and write it out and just go through that process in your head of, okay, I see that, I'm going to ignore it, and showing your work that you did take it into account, because the equation is not delta x equals 1/2 a times t squared, right? It does include this, but you're going to just knock it out anyways because the v naught is 0. Okay, so 1/2, our acceleration is 9.81 meters per second squared. And our time is 1.28 seconds, and we're going to square that. Okay. And so seconds squared is going to end up canceling, and you're going to end up with meters as your final unit. So once we do all that in our calculator, we have 8.04 meters. Okay, so we have 3 significant figures coming from both of these, and 3 significant figures in our answer. So the height of the building is 8.04 meters. And just check that I am answering what's being asked for. What is the height of the building? Height of the building, 8.04 meters is a height value, and we are good there. Question 14. A rock is thrown with velocity of 2.72 meters per second downward. What is its velocity the instant it hits the ground, which is 12.1 meters below the height from which the rock was thrown? Okay, so what we're being asked for is its velocity the instant it hits the ground. That's going to be velocity final, the final velocity, VF. Let's write out what else we know. We know the initial velocity is 2.72 meters per second downward. Notice I've highlighted downward as a vector quantity. We're going to define downward as positive. This entire thing that's happening, everything's moving down. So it's just easier to say in this case that down is positive. Okay. We know that it was thrown from 12.1 meters. So that's our delta x. And of course we know our acceleration. That's gravity. So 9.81 meters per second squared. Now, this equation up here is not going to work for this problem because we actually have every single variable in this equation. We have delta x, we have initial velocity, we have time, and acceleration. So using this wouldn't tell us anything. We would just say, yeah, delta x does equal those things. And so instead, we need to use the prior equation that is about displacement and acceleration, where we can determine what the final velocity is. Okay, we can't use this one because we don't have time, and none of the other acceleration equations will work either. Okay, so this equation is our final velocity squared equals our initial velocity squared plus 2 times acceleration times delta x. So let's plug everything in here. Okay, we have our initial velocity, 2.72 meters per second. We're going to square all of that, plus 2 times 2 times our acceleration, 9.81 meters per second squared, times 12.1 meters. Okay. And so when we calculate all of this out and make sure we have 3 significant figures, because 3 here, 3 here, 3 here, we get our velocity final squared equals 245 meters squared per second squared. Okay, we're going to take the square root of both sides. And so our final velocity equals 15.6 meters per second. And obviously going to be downward. Okay, so the final velocity is 15.6 meters per second downward. Okay, question 15. An object is in free fall for 13.1 seconds. If its final velocity is 98.6 meters per second downward, what was its initial velocity? So, what was its initial velocity? We need to know this vector quantity. Okay, so downward velocity. Okay, so I'm going to go ahead and make downward positive again. I might end up regretting it, but we'll see. And let's write what we know. So time equals 13.1 seconds. Okay, final velocity equals 98 meters per second. We know it's in free fall, so our acceleration is 9.81 meters per second squared. And is there anything else that we know from this? We know we are trying to determine the initial velocity, right? So v naught equals question mark. Okay. So let's look at our equations here. We have time, final velocity, acceleration, and we need initial velocity. And so that's four things, and that is everything here, all right? Our velocity final equals initial velocity plus acceleration times time. So let's plug that in. So Vf equals V naught plus, okay, writing the wrong equation, plus acceleration times time. Okay, let's plug everything in. 98 meters per second equals, we don't know V naught yet, plus 9.81 meters per second squared times 13.1 seconds. Okay, so seconds, one of those seconds is going to cancel out. And so we'll have 98 meters per second equals V naught plus make sure I'm getting this right. $129 meters per second. Sorry for the pause there. Making sure that I've calculated that right. And now we will subtract, okay? So I kept this 3 significant figures because I have 9.81 and 13.1. So that's 3 significant figures. Now I'm going to subtract. Now remember, my subtraction rules with significant figures has more to do with place value, not total number of significant figures, okay? So subtract 129 meters per second from both sides. Okay, I'm going to get negative 31 meters per second here equals V naught. Okay, so positive is downward. So what actually happened here was that because this is negative, this object was thrown up first before it started coming back down. due to gravity. Okay, so the initial velocity is 31 meters per second upward. Question 16. A ball is put in free fall. It ends up hitting the ground, which is 6.1 feet below where it was launched in 5.10 seconds. What was its initial velocity? Okay, so here I'm going to have my acceleration. Because I don't know if this initial velocity is that the ball was going up first, or if it was just dropped or thrown down, I'm going to go ahead and put the acceleration as negative. So negative 9.81 meters per second squared. Okay, my displacement is here, here, 6.1 feet. So delta x, it went down, right? It is below where it was launched. And so that's going to be negative also, negative 6.1 feet. And wait a second, I just realized that I messed up because my displacement's in feet and my acceleration is in meters per second squared. I'm so used to doing this 9.81 that it's kind of my second nature, but we actually need to use the acceleration, free fall acceleration units that are in feet per second squared. So it's going to be negative 32.2 feet per second squared. Okay. Other things that we know time equals 5.10 seconds. And we know that we need to know what the initial velocity is. Okay, so let's look at possible equations we can use. Okay, so this one won't work because we don't know anything about final velocity. This one won't work. We don't know anything about final velocity. This one, we know delta x, we know initial velocity, we know the acceleration. We don't know the initial velocity, we know the acceleration, and we do know the time. So this is the one that we're going to use. Delta x equals v naught times t plus 1/2. Okay, so let's plug everything in. And if you are working, so depending on your teacher, you may or may not have to have these equations memorized for an exam. So I just want to point out. So if these are not going to be given to you for your exam, then, all of this, me referencing this, should be basically done in your head at this point, because when you're doing the review questions, you really should try to have all of these equations already memorized for that. Okay, so negative 6.1 feet equals my initial velocity, which is unknown, times 5.10 seconds plus 1/2 of acceleration times time, 5.10 seconds, and we're going to square that. Okay, so when I calculate all of this, I'm going to get negative 419 feet, right? Because the seconds squared are going to cancel. Okay, and so I'm going to add 419 feet to both sides. And when I am subtracting and adding here, my significant digits should be based on place value, and we're going to use the least precise place value. So 419 feet minus 6.1 feet, I'm just going to subtract 419 minus 6 to do that. So we're going to end up with 413 feet equals V naught times 5.10 seconds. Divide by size by 5.10 seconds. And we will end up with 81.0 feet per second equals our initial velocity. Okay, so now writing that out in a sentence, it's initial velocity. This is a vector quantity, so I need to, I just wrote vector. The vector quantity, so we need to include the direction. So for this one, we put free fall. I should almost kind of define up here what my free fall is going to be, and I decided it was negative for this one. Okay, so its initial velocity is 81.0 feet per second. I decided that down was negative for this one. So this is positive, and so that means that the ball was thrown upward to start with. Okay, question 17. What is the weight of an object whose mass is 14.8 slugs? Okay, so this is going to come from our equation where weight equals mass times gravity. Okay, we're dealing with slugs, which are going to be English units. And so what do we know? The mass equals 14.8 slugs. We know our acceleration, our G, should say, is 32.2 feet per second squared. Now, when we're doing weight, even though we're dealing with acceleration due to gravity, we're not going to assign it a vector. And so we just know that this 32.2 feet per second squared is downward, and down is positive. And so we keep it positive here. Okay, so here are our weight then is 14.8 slugs times 32.2 feet per second squared, and that's going to equal 477 slugs times feet per second squared, and this equals pounds. This whole thing equals pounds. And note that that is one of the things that I wrote as something that I should know. So the weight of the object is 477 pounds. Last one, question 18. An object weighs 170 newtons on Earth. How much does it weigh on the moon, where the acceleration due to gravity is 1.6 meters per second squared? Okay, So how much does it weigh on the moon? Okay. So on Earth, we know that the acceleration due to gravity is 9.81 meters per second squared. And in order to find out what it weighs on the moon, we are going to need to find out what the mass is, okay? We know the force and the acceleration, and we know force equals mass times acceleration, so we can figure out the mass from that, and then we can figure out the weight on the moon is using the mass and the gravity on the moon, okay? So force equals mass times acceleration. 170 kilograms meters per second squared equals our mass times 9.81 meters per second squared. Okay, and we'll just go ahead and cancel the meters per second squared here and divide. So divided by 9.81, divided by 9.81, and so 170 divided by 9.81. This is two significant figures. 170 is two significant figures. So our answer here is going to be two significant figures, and it's going to be just 17 kilograms equals the mass. Okay, so that's our first step in this. And then now we can use our weight equation. Weight equals mass times the gravity. Okay, so our weights are unknown. Our mass is 17 kilograms. And our gravity is 1.6. Oops, I put it equal there. Times 1.6 meters per second squared. Okay. And once we multiply that, we're going to have two significant figures in our answer. And you have 27 kilograms times meters per second squared. That equals newtons, right? So the object weighs 27 newtons on the moon. Okay, and that is the final answer of this chapter review. Again, if you have any questions, feel free to add them in response to this video, and I or someone else, if they are in the know and see your question, will do our best ability to best we can to answer them.